Okay, I'm going to talk fast because otherwise this will be a really long video. Hopefully I don't talk too fast. So how do the flow rates at A, B, and C compare to each other? The flow rates are the same because these are series points. Flow rates are the same. Because these are elements in series, the charge only has one path, and so it all moves forward at the same rate. How do the electric pressures at A and C compare to each other? The pressure at A is greater than the pressure at C. There has to be a pressure difference in order to make charge move through the bulbs. And so I would say that we have, this is red and this is yellow. How do the flow rates at X, Y, and Z compare to each other? Well, we know that the flow has to split because I have different paths. And so there is going to be unequal flow in Y and Z. We know that, I'll just write it down, that the flow through X is going to be equal to the flow through Y plus the flow through Z. And we also know that there is going to be a greater flow rate in Y. So Y will be greater than Z because a round bulb has less resistance than L. So this is the path of less resistance, so more flow. Okay, how do the electric pressures at X, Y, and Z compare to each other? So because these are all connected by a wire and we consider those zero resistance, the pressure on all of those is the same, and specifically it is all red. So. Okay, number 2. The wires that an electric company connects to your house can be pictured as being attached to a very big battery having an electric pressure difference of 120 volts. The electric lights and appliances in your house are designed to operate properly only when there is a 120 volt pressure difference across them, and they are all connected in parallel. So what is the advantage of parallel wiring rather than series? So there are kind of 2 big reasons why we'd do this, and that is you can, you know without question that each device will get 120 volts. If they're in series, that 120 volts would split across the devices. So if we had like 1, 2, 3, so this is wrong. If we had a 120 volt battery, then we know that 120 volts, like this might be 90 and this might be 10, and then this would then become 20. So the potential would split across the devices. And so this is not what works. In parallel, each device gets 120 volts. And then the other advantage is you can turn on and off independently. On and off independently. If we have a series circuit, if I turn off one device, then everything is cut off because there's only one pathway through. Okay, a typical house has many separate circuits, each of which has multiple parallel branches. In each circuit, the trunk leading to the parallel branch is wired in series with a fuse or a circuit breaker. A fuse melts or a circuit. So let's think about what that means. So I've got in series, you know, it's often good to write down, I've got the fuse, and then this is in series with appliances. I'm just going to do one that are in parallel to each other. Now, the advantage of that is that so a fuse melts or a circuit breaker opens if the current through it becomes greater than a certain value. The purpose is to prevent the wires from overheating, possibly starting a fire. It's also to prevent appliances from being damaged. How is a fuse or circuit able to break it? So the idea is that when this gets too hot, it kind of melts or opens, and it stops the flow through this branch stops flow through this branch. And so with that in mind, and this did not come out of thin air, I was just reading the words. I've got a fuse in series with appliances that are in parallel. So in the space below, draw a schematic diagram of a house circuit containing, okay, we've got a TV, a TV, a computer, and a microwave. So we want each one of them is going to have a switch. And I'm going to connect these. So those are in parallel. Parallel. And then they are in series with a fuse. And then I have kind of I'm going to just say lines to electric company, where I would normally put my battery. And then this will go over here and be on the other side of my devices in parallel. So that's how I would draw it. You might feel more comfortable. I'm going to draw it a different way, the way that you have normally seen circuits. I will often draw my circuits twice. So here's how I would do parallel. So that's how we've seen our battery or our light bulbs look parallel. Comes up here. It's my fuse. And again here, I'm going to draw my power source as a battery, but that would go, this is 120 to electric company. Both of those are synonymous, you only need to draw one. Okay, in a house, the branch wires may be attached to appliances and bulbs of different resistance. What is the relationship between the flow rate of charge in the main trunk wire of a house and the flow rate of charge in the branch wires? So we know that the everything coming into the house splits amongst the branches, or probably the more sensible way to say it is that the sum of the branches, so in other words, sum of all the electricity used up by the appliances equals the required energy flow, or the required flow rate into the house. That's probably the smarter way to say it. Okay. Battery is connected to 3 long bulbs in series. After a steady state condition is reached, a 4th bulb is connected. Okay, this is in parallel. What effect does adding the bulb have on, okay, the pressure difference across bulb B? This is going to decrease. And basically, I'm reducing the resistance of this parallel combination. Again, it's like adding a straw side by side. When you add straws side by side, you can blow more air to it. So I'm reducing the resistance, and so that means that the voltage division will result in less pressure difference across the parallel pair. Okay, B, the flow rate through bulb B will also decrease, again because the pressure difference driving it is also decreased. C, the pressure difference across bulb A will actually increase, and this is because if I've got more flow through this parallel combination, that means I've got more flow through the circuit. And so therefore that has to increase the pressure difference across bulb A. And then D, the total or net resistance of the circuit has decreased. If you decrease one part of it, you generally will decrease everything. And then hopefully you actually did this. If you did not do that yesterday, then you definitely should, so that you can see kind of the differences in bulb brightness. That will help confirm your answers. If you didn't do it yesterday, do it. All right, refer to the same circuit. Instead of adding a long bulb parallel to bulb B, consider adding a wire. Okay, so we are now going to short this out by adding a wire. And so remember, basically flow through here is going to cease. So the pressure difference across bulb B will basically go to 0. Flow rate through bulb B will go to 0 because there's no pressure. Pressure difference across bulb A will increase because I've got more flow. Remember, I've got tons and tons of flow through this circuit because it's basically you're turning a 3-bulb circuit into a 2-bulb circuit. And so the total or net resistance of the circuit will decrease. That's why we've got more flow. All right, hopefully that made sense. All right, this is the one that is challenging, so I'm gonna have to think about this. All right, so let's do we know that this is gonna be red. This is gonna be red. And then we know the bottom is gonna be blue. Okay, so I think that, where are we? I think that this wire is going to be orange. And this wire is going to be green. And the reason why is because this is a dim bulb and this is a dim bulb, or it's dimmer than the long bulbs. And so I need to have less of a pressure difference across here than I do across here. Same thing, I need to have less of a pressure difference across here than across here, because that's how I make the long bulbs brighter, is through the pressure differential. And remember, we've got Roy G. B. Oops, B. Okay. So that is my initial color. And then, all right, so that, then in figure B, we've still got red. And I think that all the middle wires are going to be yellow. Because when I short across, everything should be the same brightness. Okay, B. So the flow in the added wire, the moment the wire is connected, I see that this is orange and this is green, and so the flow has to be to the right. This way, because it's lower pressure. Okay, which way will the charge flow in the added wire when a final steady state condition is reached, to the right, or the left? And I think that it will still continue to be to the right, because I'm going to call this round bulb 2. Round bulb 2 has lower resistance than long bulb 2, then L2, and so the flow will go through path of lesser resistance. And I'm going to say the majority majority of flow. L2 will still be lit, so. All right, describe the changes in bulb brightness that occur when the wire is added in B. Explain the change in brightness in terms of the change in pressure differences across the bulb. So initially the long bulbs are bright and the round ones are dim because of the way we did the pressure difference. And we did the pressure difference that way because we've worked with the long bulbs and the round bulbs, and we know which one has greater resistance. So with the added wire in place, all the bulbs have the same pressure difference. So this is an increase in pressure difference across the round bulbs, and so they become brighter. And it's a decrease in pressure difference across the long bulbs, and so they are going to become dimmer. All right, is a battery a device which supplies a constant current to a circuit? And the answer to this is no. It depends on the resistance of the circuit. So when I have less resistance, like if I just use a wire, then there can be like a very large current, as opposed to if I have a bunch of bulbs, then it will, the current will be much less. So the battery does not provide constant current because it depends on the resistance. Is a battery a device which supplies a constant electric pressure to a circuit? We would say typically or ordinarily yes. But if there's very little resistance in the circuit, such as when you are shorting a wire, then the pressure difference across the terminals may be reduced to essentially zero. So you just have like major flow. So, all right, color code 10A and 10B once the circuits have reached a steady state. All right. Again, this takes me a little while to think about it. So I know that this is red, red, and we've got blue, and we've got blue. I'm going to do the right one first because it's the easier one. Okay. So I know that the middle wire is going to be yellow. I goofed on this. I was wondering why was I mystified by that. Sorry about that. That should be green. Green. And yellow in the middle. I got a little bit happy there. And then orange. Okay. All right. So once I have reached steady state, I'm going to have to think about this. I know that I have no flow through here, and all of the flow is going through here, but this needs to be the same color. I'm going to come back to that one. I'm going to try to talk my way through this. Explain why the circuit in figure 10B requires much less time to reach the final steady state without a capacitor in the circuit as it is in figure 10A. All right, so that one is easy to answer. So 10B has a lot less metal. So it reaches steady state much faster. The capacitor, remember, it's basically like two huge sheets of metal that are, there's an insulator between them. So remember the capacitor, I've got a conductor, I've got the insulator, and I've got the conductor. And these are rolled into this with the two terminals. I haven't really showed you this, but there's just like a stunning amount of metal that is rolled up into this capacitor. And so that's why it takes a long time to reach steady state. All right, I'm going to get back to you on the colors for this just because I need to think about this and I don't want to say anything wrong. So I will let you guys know. I'll probably send an email. Ah, that was it.